Okay, so here's another condition where we have an object that is hanging from the ceiling and connected with strings as shown here in our diagram. Okay, so let's call this one string number 1 and this is string number 2. Some of you might want to use a string 1 and string 2, so whatever the problem will give you. It just so happened that I'm used to using the right side as number 1 here in every illustration. However, sometimes I use 1 on the left side and 2 on the right side, so it all depends on your preference. However, you will still get the same analysis. Okay, now this time let's solve for tension number 1 and tension number 2 with a condition that the angles are the same. So this one, it's a little bit more, I would say, easy. Okay, so less complicated because the angles are the same. So the angles are the same, and if they're identical, of course, you have the identical values. Okay, so what do I mean by having identical values? So why don't we just start with our solution, and then of course we all know that the acceleration is both 0 on both the x and y coordinates. X, y, or y and x, both of them are 0. Why are they 0? Because the condition. Not unless you cut the string and then it will start to move. Okay. Now, let us begin. So of course, the first thing that we should do is your free body diagram. And before we start our free body diagram, and if you notice, even in this angle, even in this illustration, the angles were already transferred here, even though we all know that the angle over here is the same as the angle on this side. Okay. As I mentioned in the last or the most recent video, I said to just please pay attention to our math teachers as they were explaining about triangles. So, free body diagrams. Again, where's the intersection of forces? So we have our intersection of forces is going to be right here. And if I have my force of gravity downward, which is our weight, F of g, and then we have two identical forces. So let's say these are the two forces that I have. And then we have this one right here. Again, as I mentioned earlier in the previous video, it's better to use just t instead of f of t, even though f of t is still possible to use. The only issue about using the f of t, subscript after subscript after subscript. So this one is 1, and this is our tension 2. So tension 1 and tension 2. There we go. Next, part of our solution. Part of our solution is to draw another free body diagram. Okay, so let's draw another free body diagram, this time with the components of the forces, which have components. In our case, that is your tension because it's not along the y or x axis. So let us draw this right here, and allow me to draw our f of g. And that f of g is simply equivalent to mass of g. So we can basically draw this one again, and then let's analyze and see the difference or any similarities. Now, if I have my t sub 1 right here and t sub 2 over here, and the angles are the same, t sub, so that both of them are theta, what we can say here is that if we use the blue on the right side or left side, so these are the components for t sub 2, and here are the components of t sub 1. Right away, because they have the same angle, we notice that these two triangles that you form on each side of our setup of our system are identical because you have the same angle. So you have the same angle, you would have the same components. Okay, so you would have the same components, or magnitude of the components, and magnitude of the actual force. And what do we have here? So we can say that if this is t sub 2x or y, and this is t sub 2x, and of course the right side we have the green dotted lines, which are the components of one along the y-axis and one along the x-axis. By looking at this, since they're identical, same angles, triangles are identical, figures are identical. Okay, so identical. So what can we say over here? That t sub 2x or t sub 2y is equal to t sub 2 t sub 1y, which we can just say, oh, same thing. So t of y, and then t sub 2 x is the same as t sub 1x, then we can just call it t sub x. Okay, t of x. Okay, so we can just call it t sub x on both of them. Now if we are going to draw another free body diagram on the other side right here so we can see it. Okay, so right here, I'll draw it again, where f of g is simply equivalent to mg. And then let us draw the blue side, which is our t sub 1, t sub 2. We can also call it as t. So here are different components. I have this as t of x, and on this side we have t of x. And then when you subtract those forces, definitely we'll get 0. So they're equal. Okay, so t sub x, they're the same. So we don't even have to analyze the x component here, the forces acting on the x component, because by looking at this, we all know that they're identical. So if they're identical, so it will give us 0. So you don't need to work on that process. But some of you might want to show it. You can definitely show it. Next, and I got too excited in using blue, but you know what? Let's just use this for green. Let me just write over it. Hopefully you can still see the green. Right here we have our green side, which is our t of y. And then we have the blue side with t of y. So they are the same component. So they have the same magnitude. So by just looking at the scale of free body diagrams that we draw, I have 2 sections on each side. So 2 plus 2, that's 4. How many do we have here? So we have 4. So they're balanced. They will not move. Okay, so you have a balanced force. Okay, balance force, a net force of 0. Now let's proceed with a very simple solution right here. You can say that the summation of forces along the y-axis is simply equivalent to mass times the acceleration due to gravity along the y-axis, which is 0, as we have indicated here. So we can just say the different forces positive going up. So t sub y blue plus t sub y green minus f of g equals 0. So we have what? T sub y, they're the same. So I can just say that these are 2 tension minus mass times g equals 0. Moving the force of gravity to the other side of the equation, from negative, now it's going to be positive, t sub y. So that is m of g. So what does it mean? For each section, you have 1/2 of the mass. So it's equally distributed because of having an identical angle. So we can say that t sub y That is mg over 2. So therefore, we can say that each of those forces acting along the y-axis is basically the same. Now, this is y. But what is the actual tension? We all know again that that the angle is measured along the x-axis. So it means that the y component is basically whatever the tension is, you multiply it by the sine of the angle. So this will give us mg over 2. Again, we don't need sine to be together with the tension. So we want to figure out the tension by itself. So that is mg 2 sine theta. So it means that the magnitude of t sub 1 is the same as t, which is mg 2 sine theta, and t sub 2 is also equivalent to t, mg 2 sine theta. Okay, so if we notice, I draw a box around this. However, this is not your final answer. Do not stop here, because the question is, what is t sub 1 and t sub 2? You were able to figure out that t sub 1 and t sub 2 are the same. To get full credit, you must explain that t sub 1 is the same as t sub 1, or tension on the right side is the same as the tension on the right side, on the left side. And they're identical, so that's why we're placing it as the same t. So it's 1/2 of the total load, which is the mass multiplied by the gravitational field strength. So do not stop here. Continue in showing your solution, stating that this is your answer for both string on the right side, which is number 1, and string on the left side, which is string number